Hi folks, welcome back to Physics with Captain Rod. This video is intended to be video 2 on a video series of how to analyze structures. So what we're looking at, we've got this frame connected at the following points here, kind of a solid connection here at C, kind of a roller connection here at B, acting with the following loads: the 600 Newton force to the right, 400 Newton force down. What I'm going to do in this video, to keep the video kind of short, I'm going to go after the internal force developed here between A and D, and that's pretty well all I'm going to do. I don't want to keep these. I want to keep these things to reasonable lengths here. So the first thing when analyzing a structure you usually do is you start with the free body of the entire system. So the first thing I'm going to do is put a reaction force here at C. And I'm just going to not even think about the direction here. I'm just going to assume a right positive. So there's a CX. And also C can support that structure vertically. So I'm going to put a vertical force there. Upward. CY. No moment reactions at C because of how this is connected. This is a pin. If this were welded or something like that, then yeah, then you could have a moment reaction here. But with a pin at that point, C cannot support any sort of moment reaction. All right, looking at point A, this thing's resting on the ground here. So point A, it makes sense to put a vertical force there, AY. But this thing's allowed to roll back and forth, so we can't put, there can't be a horizontal force reaction at point A, nor can there be any sort of moments or anything like that. So that's pretty well it. Our free body of the structure is pretty well done. Now I'm going to start writing equations to try to find those reaction forces. I'm going to go ahead and find AY first, and you'll notice that both of these unknowns go through C. So a good place to start would be sum of all moments about C equals 0. Right? And again, in green here, calling this point C, or in red. The reason to start there is because neither of these forces create moment about that point. That'll give me a nice easy equation for AY. So moment produced by AY about C. Now AY acts all along this line. The moment arm for AY is this distance, which is 6 meters. So equation-wise, we're going to have minus AY times 6 meters. Minus because AY is producing clockwise moment about C. All right, next force producing moment, this 400 newtons, that's producing clockwise moment. I'm sorry, counterclockwise moment, and I'm calling counterclockwise positive, so we're going to have plus 400 newtons times 3 meters. Next force to consider is this 600 newtons here. Boy, I'm running out of room. This computer I use is kind of cool for this. Need a little more room to write my equation there. All right, so now the moment produced by the 600 newtons acts all along this line. The moment arm for the 600 is this distance. Make sure it's clear in green. That's the distance for the 600 newtons. That is 4 meters. So we're going to have plus 600 newtons times 4 meters. And that's it. Those are all the forces creating moment about C. So equals 0. So AY is going to equal, let's see, if we solve that for AY, I'm going to go ahead and just get a calculator out because it's late in the day. So all right, so I get 600 newtons positive. Yep, that looks right. Okay. All right, now that we have AY, it's pretty easy to get CY. We can use a force equation to get CY. Sum of all forces, y direction equals 0. Up positive, that's going to be CY plus AY minus 400 newtons for this. This guy does not have a y component, so that's going to be equal 0. So let's see, we're after CY is going to be 400 newtons minus AY. So CY, it looks like, is minus 200 newtons. Nothing wrong with that. That just means opposite direction shown. And then sum of all forces x direction, and I'm not going to write this. Oh, yeah, I guess I will write it down. Sum of all forces x direction equals 0, right positive. That's going to be CX plus 600 newtons for this force at D equals 0. So Cx is equal to minus 600 newtons. At first I wasn't going to write it down because I forgot about this force here. Had that force not been there, I would have just written down Cx equals 0 and moved on. But then I noticed there's a force there, so I went ahead and wrote that equation out. All right, so now what we need to do is we need to get rid of the stuff we don't need. So again, anybody who wants to can go back through the video and see how these were calculated, but I don't need these equations anymore, and I need the room. So I'm going to get rid of that. This. This. And then I'm just going to store this information up here to give myself room to work. All right, reactions are known. Now, again, in the video here, I mentioned I'm only going to go after one force component here. I'm going to get the internal force here between A and D. The reason I'm doing that is I just want to keep these videos short. And I'm also going to avoid what I would call probably the easiest method to get it. I mean, there's different ways to do this, and I want to talk about the different ways we could go after that force component. One, we could, if we wanted to, do something like this. We could draw a free body of this connection point. Remember that the reactions are known, so what that will do for us is it will find force CB, and it'll find for us force CD. Then we could do a free body of this joint, keeping in mind that force CD is known. That would allow us to calculate force BD and force AD, and we'd be done. That's, one way to go about doing it. All right, well, one of the things I wanted to do is I wanted to highlight how to apply what's called methods of sections. When you do a free body of a joint, it's called method of joints. When you do a free body of a section, it's called free body of, or method of sections. So what I'm going to do is a free body of this. And you notice that the force that I want, AD, goes across that boundary here. So what will happen is I'll draw my free body, then I'll figure out how to use my free body to find that force. So when we draw a free body, you should always draw the structure in question. So I'm going to cut it right there. I'm going to include that force. It's easier for me to do on a computer than it is for somebody working this with your homework. Copy, because you have to actually redraw it. Oh boy, something went wrong there. Oops. Lasso. Alright, so what I want to do here is I want to come right through here. Why is that doing that? There, that should work. Copy. Paste. This thing seems to be kind of giving me not behaving quite the way I think. All right, I think that's good enough. All right, so I've recopied this. Now I got to start putting force vectors back in. There's that 600, and then right here to the right, whoops, we got CX. Now I know it came out negative, but I'm being consistent with my original picture. Vertical force up, CY. Again, it came out negative. Just be consistent with your original picture. We've got this 400 Newton-pound force acting down at that point. Now, we don't need to worry about any forces within these because these are internal to my system the way I've defined it. We do have a force between A and D, and again, assuming tension, that force is this way, FAB. I might have said AD a minute ago, but I meant between A and B. We also now have a force between A and D, and remember what our free body is of, and I'm going to assume tension. Oops. That force should be, right like this. There we go. FAD. And that's the one I'm looking for here in this example. Now, this free body has two unknowns, force AB, force AD. We can solve it guaranteed. There's only two unknowns, and we can write, three equations for this, two force and one moment equation. I'm going to try to get to force AB with the quickest I possibly can. And what I'm going to do is I'm going to write a moment equation, all right, sum of all moments, and I'm going to write it about point B equals 0, counterclockwise positive. Now, what's so cool about using point B? Well, neither of these forces go through B. So by writing that moment equation about this point, I won't have to find force AB, so it'll be shorter. And you'll notice that this thing's got some angles. I'd have to kind of deal with that. Not super tough, but if I pick that point, I don't need to worry about these two forces. The only thing that will show up in the moment equations are these four. Actually, these three. Force AB will show up, force CY, the 600 newtons, but CX also backtracks right through point B, so that won't show up either. So I'm going to go ahead and write that moment equation starting with this. So we're going to have, force AD times, now I need this distance, which I'm going to get from right here, 4 meters. And that moment is negative because this force makes this structure want to rotate clockwise about this point. That's a negative, negative moment. All right, then we're going to have plus 600 newtons times the same distance, 4 meters, for this force. Moment produced by CX is 0 because it goes right through B. Then we're going to have this force plus CY, which I know, times this distance, 3 meters. And I think that's it. I think that equals 0. Just make sure 1, 2, 3 terms for about that point. Yep, I think it looks good. All right, so now what we just need to do is put in numerical values. We know that CY is minus 200. So what you do is you're going to sub negative 200 right here, negative 200 newtons, and then solve that for force AD. So I'm not going to bother rewriting it because I'm pretty much out of room. I'm just going to go ahead and solve it here. And what I got out of this is that force AD, I got a positive 450 newtons out of the solution of that equation. And again, the positive sign is indicating tension because I assumed tension. It came out positive. The positive sign means my assumed direction is correct. So again, this is meant to be video number 2 on analyzing structures. It's meant to be just a tiny bit more complex than the previous video, and then video number 3 will probably be just a tiny bit more complex. The big part about analyzing structures, it really boils down to this. Usually you start with a free body of the entire structure. Write force and moment equations until you have all the reactions. Then usually what you do is, at your choice. You can either draw free bodies of the connections, like maybe this, or this, or this, and then you can write systems of equations at each connection point, and you can kind of march through the structure. So what I mean by that is, once you know CX and CY, you do a free body of this. Now you know the force in this beam and this beam, which means you could maybe move here, calculate the force here, and then maybe move here and get the last one. Or you can do what I did, and you can do a free body of a section of the structure. So in this case, I did a free body of this section, and you'll notice that the force I was interested in crossed that boundary. Then I was able to cleverly choose, maybe not so clever, but choose a point some moments about to get that force with a single equation. So anyway, method of sections, very powerful method. Method of joints, very powerful method. And the idea is to be able to use both. Hope this video helps demonstrate these concepts. Have a great day.